and expects that at least the senior members of the audience will know more or less everything about all the details that I'm going to talk about, but possibly it would be less pressurizing, let's say this way, for those who are still learning. Okay, so let me start with matrix system. This is something that everyone knows, right? We are not Heisenbergs, right? What Heisenberg invented in what was the so-called matrix quantum mechanics, because not a single idea of the very concept of matrices. So, and for that he was awarded the Nobel Prize. Yeah, I think so. So, but we're better than Heisenberg, therefore. So actually, we do know something about matrices. So let me start with Euclidean space E, which is a finite dimensional linear space within a product. And let me consider a matrix there, A. It's a darkness.
You need to press on it. It's coming on.
Does it work out?
Yeah.
The other people have already talked a lot about operators. So a matrix is an operator, of course. More or less, moreover, any operator in a finite dimensional linear space is a matrix. Okay, thank you. Maybe this is better. Let's try it. So this is a very particular example of operators. When I pass over to the operators, which will happen anytime soon, in fact, I will just say that any at least bounded operator in a Hilbert space can be realized as a matrix as well. The only difference is going to be that this matrix is going to be infinite dimensional. It's not that simple for unbounded operators like differential ones, which are to be found in mathematical physics. Although you still can sort of perceive any operator as an infinite matrix, as simple as that. So those matrices, they do have spectra. And let me remind you that the spectrum of a matrix is the set of points lambda such that there exists no inverse to A minus C to A minus lambda 1, right? So this is the spectrum. What I'm going to assume about the matrix, with little or no loss of generality so far, I will assume that the matrix is Hermitian, which means that the Hermitian conjugate of the matrix is precisely equal to the matrix itself. Since I'm in the Euclidean case, I can rewrite that in the following way. So if my inner product is denoted by angle brackets, then I can say that the matrix is Hermitian if and only for any x and y in my space. The equality now holds. So this is an all even if thing. So I'm going to refer to those guys as self-adjoint matrices, by the way, because this is the way I prefer it to be. So Hermitian and self-adjoint are the same thing. By definition. And now I'm going to consider the thing which has been referred to Hermitian matrix by definition of self-adjoint. Technically, you are correct, yes. But normally, well, these days, most people won't call it differentiated. It's just two different groups for the same thing. Right, anyway, so so the spectrum is here, the self-adjoint is coherence, or the property of the definition is here. And what do I need? I need a resolvent. So this is again the term that has been used before by many speakers. So the resolvent is precisely the inverse of this guy. So for any lambda, for any lambda for which it is possible, I will consider the inverse matrix defined like that. So everywhere, except on the spectrum, which is just a final set of points in the context plane, this is well defined. It's also a finite matrix.
So in the definition of spectrum, that does not exist.
Oh, sorry about that. Thank you. So it's I said it correctly, but I have written correctly, right? Yeah. So this is well defined, except for a certain set of points, a finite set of points in the context plane. And now I need a projection as well. So what is a projection? A projection is by definition an operator, aka a matrix, in fact, which has precisely one property, and this property is this: p squared is equal to p. So if you apply it twice, which is denoted as usual as the application of a square of the it leaves you where you were, right? So you apply it once, then you apply it twice, but the second application leaves you where you are. So that means that an operator is a projection. And loosely speaking, again, you will probably argue against this case. But loosely speaking, I want to say that a projection matrix is a matrix which has the same property. So because again, I have the inner product structure, because I'm working in the Euclidean space, I have the inner product, and therefore I have orthogonality. So I can say that two vectors or two elements of my Euclidean space are orthogonal even only their inner product is equal to 0. Which allows me to introduce the so-called orthogonal projection, which is firstly this, and secondly, it has to be Hermitian. So if you have a collection of these two properties, that leaves you with an orthogonal projection. This is very simple to ascertain on the basis of geometry. So probably everything knows all of it. And now my question is this. Let me mix everything up together. Let me consider the following object. I will take any Hermitian matrix, I will take its resolvent, and I will border this resolvent by two projections, like that. I will take an orthogonal projection E, which is generally speaking unrelated to my matrix A, and I will consider an object like that. Well, first of all, it's also a matrix. So it's again a linear iterator in the same finite dimensional Euclidean space. But and now the question is, and the subject of my talk is, how do you classify that? What is it? Maybe it's also a resolvent of some other matrix. Can that happen? Just to begin with, let's check. That's the simple part. So for Hermitian matrices, same as for self-adjoint iterators, I have the so-called spectral theorem, which I hope everyone knows. It basically tells you that if your matrix is Hermitian, then you can rewrite this matrix in the following way. It's a sum of lambda j's belonging to the spectrum of the matrix A of lambda j's themselves multiplied by the so-called spectral projections onto the eigenspaces associated with these particular values of the spectral parameter lambda. From there, you know what how to rewrite the resolvent of the matrix A. And quite obviously, the resolvent of the matrix A will be the following representation. It will be still the same sum, this is sum, over lambda j in the spectrum of the matrix A of 1 over lambda j minus lambda tj. Again, this is a finite sum, no problem with that. In general, if we pass over, and we will eventually pass over to unbounded operators in Hilbert spaces, all those sums and the statements themselves actually survive, but the sums have to be replaced by integrals. It's as simple as that. So even if I write an integral of this type later on in my talk, you will know what it means for matrices at least. So as a reference point, you always can think about matrices. So you do that, and from that it is easily seen what is the condition for this guy to be a resolvent of some other self-adjoint or dimension matrix. Of course, P has to be one of the spectral projections of this guy, of A. So, so for A minus lambda 1 minus 1 to be, so B to be equal to, say, B minus lambda 1 minus 1 inverse, right? For some condition B in the same space, it is necessary and sufficient for B to be of the form sum over some collection of j's Pj. So you can either take any single spectral projection or any sum of them, because any sum of them, they are all mutually orthogonal, is also a spectral projection. Yep.
You know, if you look at P and the resolvent, he's really a projection. Then for any lambda, your operator has a null state. Yeah, so it can't really be the resolvent, but you project it to the image.
Yeah.
And you need to say something about that.
Well,
Yes, you will.
So technically speaking, yes, the point made by Stephen is precisely is correct, because I mean, if I now pass over to a simple operation, I'll take just P1. So now P1 is the spectral projection of this particular matrix A, and if you consider that, then of course this guy will have a matrix structure like that. It will be something here, and we know what, but zero elsewhere. So it means that this guy will, of course, be a resolvent of some self-adjoint matrix, but in a smaller space. And the smaller space will be given, well, remember that I have started with the Euclidean space E, And the smallest space, say E1, is just defined by P1E in this case, right? Still, the answer is the same, right? So it's you can actually do it as a homework if you wish. This is a very simple statement, right? So it's an if and only if situation. For that to be a resolvent itself, you need to be your P to somehow be related in a very specific way to your original operator A. You need P to be one of its spectral projections. And again, this proof can be carried over in a very simple way because you also have the spectral theory for self-adjoint operators in Hilbert spaces. With the same proof, it carries over to the situation of probably even unbounded, but self-adjoint operators in Hilbert spaces. So there is no problem in that. So this is the first possibility which certainly can be realized. Here it is. Now, what about any other possibilities? Let's put it this way. Let's put the question so in this particular form, right? Which are the other possibilities? So we know that this guy can become a resolvent of another Hermitian matrix or self-adjoint operator. Well, can it be anything else? So can it be related to, let's say, can it be a resolvent of a non-Hermitian operator, probably? Or not self-adjoint operator? It turns out that the answer is yes. But the answer is much more complicated, and this is somehow a very funny moment where you might start with a matrix or even a scalar, in fact. So a matrix of the order 1 by 1, right, of that size, and end up with a self-adjoint operator, unbounded operator in a Hilbert space. This is precisely what the Polish theorem, which I will talk demonstrate in a moment, use. So now I have to leave oh yeah, sorry, thank you. So I will have to leave the subject of matrices for a moment. And let me see what happens in a much more general setup of self-adjoint operators in Hilbert space. So once again, a Hilbert space is the same as the Euclidean one. The only difference is the dimension. In the Euclidean case, the dimension is finite. In the Hilbert case, the dimension is infinite. Okay, there are some minute details, but I will skip them for now. They're really minute by bit, so why not? So, so let me start with a self-adjoint operator in H at Hilbert space. And same question. And the first part of the answer has already been obtained. So I have a projection, an orthogonal projection on H. And I'm considering this guy P A of, let me put Z here for the spectral parameter. I will probably use lambdas for a spectral parameter of a matrix and Z's for a spectral parameter of an operator. Just for the sake of it, I don't know. So this is the same object now. What is it? Can it be anything but a resolvent of a self-adjoint operator again in either finite dimensional or infinite dimensional space? And the answer is actually yes. But it's not so simple. So you can actually have something like that. For a very specific class of L, look, since E is a spectral projection, or maybe not, it's just any projection for the time being, right? Because it's a projection, it can be finite dimensional projection, no problem. So this guy on the right can be a matrix. Why not? Moreover, if it's a one-dimensional projection, then it can be a scalar function. Also no problem. But it can be also an operator in an infinite dimensional space on its own right. Why not? So nothing is speculated here. And it turns out that if I'm only asking for this particular condition to hold for all of these in the lower half plane of the complex plane, then this is called a dilation condition, in fact. And that can be realized for any, in fact, for any dissipative element. And of course, there is an adjoint condition because you can pass to adjoints in this line. And then you can say that if you require something like that to happen, for all these in the upper half plane, then that might happen, that might be realized, in fact, for any anti-dissipative matrix or operator on scalar A. Now, what do I mean by telling you by using this term dissipative or anti-dissipative, right? For matrices, it's simple. So A is dissipative if and only if the imaginary part of L is greater than 0. Same as before, A is anti-dissipative if and only if the imaginary part of L is less or equal than 0. You can pass over from a dissipative matrix operator to the anti-dissipative one by taking an adjoint. So if you take an adjoint from a dissipative operator or a matrix, you get an anti-dissipative one. The second adjoint will get the
What's the imaginary part of the matrix?
What's the imaginary part of the matrix? It's defined as usual. So an imaginary part of L is defined as A minus L star divided by 1.
So when you say divide, you can multiply by 1.
Yeah, but you can divide matrices by scalars.
So it means multiply.
Yes, precisely. By definition, yes.
When you say that this thing here is basically an indicator of
No. It has nothing to do with equation of gender. Or this part. Absolutely. This part has something to do with the names of Lipschitz, and that's defined in and Polish. So Lipschitz is a great Russian mathematician. Simplified realized that's one first. There's two surveys, which is okay for Spanish people.
I guess what I think that this is basically the theorem they use.
Not quite. Not quite. They use it for generalized resolvents. This is not a generalized resolvent. It's a particular case. I'm moving in that direction, slowly but surely. Okay, so what is a dissipative operator physically? A dissipative operator, you can use it. It's an operator. In fact, tells you something about what describes your system, which loses energy. So the energy does not conserve. For the energy to be conserved, you need either a measure of some or the one which is similar to the third condition, right? This is an even case. And this is a operator which is not so rigid because all this is the engineering company. But that is not very interesting part of the story. So So for this dissipative operator, if it's used as a Hamiltonian of some physical system, it tells you that basically the system dissipates energy outside. So it's like cools down in a sense. And if the system is described by an antidissipative Hamiltonian, that would mean that you are actually pumping the energy from outside into the system. So it's like, it's becoming more and more energetic in a sense. But if you think that you can do both things at the same time, then please think twice. So if you have a channel by which you supply the energy to the system, and at the same time, you have another channel by which the energy is allowed to go outside of the system, that such Hamiltonian or such system will never be described by anything, even distantly related to a distant variable. So that in that situation it will be always not dissipated, even if the total energy of the system goes down. So this is a very simple. This is a crucial of information which you have to keep in mind. So we're not talking about the total energy of the system going up or down. We're talking about the energy channel somehow. So you don't supply your system with an energy. It only dissipates locally everywhere. Then it's going to be dissipated. Even if the total energy goes down, it might lose dissipativity. Very simple so. And the very simply so, and the properties of that analytically and mathematically will be totally different. So again, and now to Fourier, so let's name some names. So first of all, there is a very nice book, which is untraditional in this area, available in English, by Lipschitz. I will give you in a few minutes' time a reference to Holland, which and the article of the paper of Holland actually contains a very nice list of references to whatever is available in English by Lipschitz. That's about 10%, I would say, of the total heritage of that guy. And then, although both Generalised and Fourier were working together in Hungary, I had no idea about what Lipschitz was doing. They did something of their own. And it all ended up in the following thing. In the following theorem, which is usually credited these days to Schiphol, and Fourier, but in fact it can be taken, well, it's a rather immediate consequence of a much older theorem by Naimark. And Naimark was working in 1940 and 1943. There was a war around. I have no idea how he managed to publish papers in 1943, quite frankly. So basically, that seminal paper, which I wholeheartedly recommend to you to read, which was published in 1943. Unfortunately, up to this date, it's not available in any language apart from Russian. So a Russian version can be supplied, no problem. It's available online. But that's about it. Some of the information from the earlier paper, which dates back to 1940, by the same guy Naimark, has appeared actually in English in an annex to the very well-known textbook on the operator theory by Achilles and Glassman. But unfortunately, they don't even touch upon the further results by Naimark. So it's actually unknown even to, I would say, 90% of the Russian mathematical audience that the operator generalization of the Kepler's representation theorem for our functions was in fact obtained by Naimark. It's usually credited to some other guys. That's the way it is, you see. So anyway, so Naimark started that whole business, I would say. This is mostly unknown up to now, apart from people apart from, well, I'm not talking about such because no, this is also.
I think now he used that.
Yes.
Basically,
He called it both, decided both ideas and Glassman and original. Yes, and additional. So anyway, so the theorem, which eventually was proved, like they were probably the third people to prove it out of many. By Signified and Foish. I'm not against Signified and Foish. They're both great mathematicians. They have no idea that something in that direction can be already done. And they have furthered this science, this area of science, very much so beyond what Naimark was had ever anticipated, quite frankly. So anyway, so they proved the following: regardless what you have here, if it's dissipative, if L is dissipative, if L is either a dissipative matrix or a dissipative operator, then there is always a self-adjoint operator in a larger space such that this holds for all Z's in the lower half plane. And of course, the dual result about the upper half plane holds automatically by conjugation. Moreover, and this is actually a funny thing, you see, you can start with a matrix L here, like a 2 by 2, no problem. But what you end up with must be an operator in a Hilbert, which means infinite dimensional space, even for matrices on the right hand side. This is the so-called the celebrated Foish theorem, which tells you that, well, such A is called dilation, and such this larger space in which it acts, in which A acts, is called a dilation space. Dilation is a natural term here. So, so the Foish theorem claims that whichever dissipative L you take here on the right, the spectrum of this guy will be absolutely continuous, purely absolutely continuous, and will cover the whole real line. Of course, for matrices, this is unthinkable. You can't have a matrix with absolutely continuous spectrum, you see. That's too much for a matrix to ask for.
On the whole line.
On the whole line. There are no gaps. The whole line is precisely this. Yeah, and it's purely absolutely continuous, nothing else. This is the Foish theorem for you, and this is a really hard result. This is very amazing. There have been a few alternative proofs that appeared over the years, and the latest one was actually constructed by Sabrina Hoka in the last, I think, 2 years. I think that one is the simplest one. Oh, but I might be biased, of course. But anyway, so this is a very hard analytic result, because I mean, in order to construct a dilation, any dilation, this is just linear algebra. You can do it as a homework. This is very simple. You just construct something in a good diagonal form, and that's it. And you basically know how to do that. There are lots of ways to do it, in fact. But in order to prove an analytic result of the nature, of that nature, like the Foish theorem, as I told you, you need to prove, you need to reflect like that. Okay, anyway. So then coming back to the subject of my talk, which I will have still a few minutes to cover. Let me pass over to the third possibility. So we've discussed two possibilities already. The first possibility was finite dimensional all the way through. The second possibility also already brings us to the subject area of self-adjoint operators and Hilbert spaces. Now, what about the third possibility? So what if neither of the opportunities is in fact realized? So it's neither a self-adjoint resolvent, nor it is a discrete resolvent. Then, as usual, we have to we have to resort to Lipschitz, who all the way back in 1957 introduced the so-called there are many names for this object, but I will pick one, a Lipschitz function. So what you do is this: you take a matrix, you can take a matrix as we will, a self-adjoint matrix. And then what you need to do the following. You need to take its resolvent and sandwich it in between two orthogonal projections as usual. And then you can in fact show that this thing, which I will denote R of lambda, has many nice analytic properties, which I will skip for now. Doesn't matter too much, but then you can show that in fact so what you do is this. So let us follow that. So your original E space in which A is acting is of course decomposable into an orthogonal sum of PE orthogonal plus P orthogonal, right? Two orthogonal complements. And if your A corresponding to this orthogonal decomposition can be realized as a log matrix of the following form. This is T, this is some R is taken here. And there are two here which have to be adjoined to each other, you see, because it's self-adjoint by definition. So this guy T has to be self-adjoint as well. And now you consider the following guy: G of Z is going to be precisely T of minus C. So it's the resolvent of that part. So essentially T can be kind of well, okay, it's actually, well, for matrices, I am allowed to do that. I can say this is just the definition. This is also a matrix in a lower dimensional space, right? And now it turns out that there exists, well, for matrices it's simple, but it also calls for operators, by the way. But there exists the following guy. There exists an operator or matrix D of Z. It depends on D of lambda, sorry. D of lambda. And this is lambda as well, sorry about that. And this is lambda. Where else? That's it. So there exists for almost all lambda, okay. Apart from a fixed finite set, there exists this matrix function D of lambda, such that R of lambda everywhere where it makes sense admits the following representation. It's nothing but D of lambda minus lambda inverse. Something like that. And this D of lambda now is called the Lipschitz function. So this is the Lipschitz function.
R is the T
this one is still is needed, but haven't been used.
What's the R?
It's that one. It's my sandwich. Lipschitz function. Lipschitz matrix, whatever you call it. And then it turns out that there is a very nice property which we have for that. And this property is this. The B of lambda admits the following representation. it's equal to T tilde minus, and I don't want to make a mistake here, minus gamma star G of lambda gamma. So this is the formula which is traceable back to the verse of Lipschitz. And now let's see what happens. So how this idea has been used. So this idea has been used extensively. In fact, Holland uses it in the analysis of embedded diagrams on the symmetric spectrum. So this is Holland. So it's usable well beyond the ideas by Lipschitz. In fact, Lipschitz has presented this speed in the setup of scattering theory as well. But he was using scattering, he was interested in scattering theory for non-self-adjoint operators. And this is pretty much the building block for the so-called Lipschitz characteristic function, which is applicable to both matrices and operators. No problem. So this is it. Now let us look at this formula.
This is the third complement.
It is, yes, you can get it out. Yes, you can actually get it out of the short continuous inertial formula. One of the ways to do it, and I think Holland does it precisely that way. But there are, it's just linear algebra here. You do it the way you prefer to. I mean, lots of different proofs are available. This is just algebra, nothing more. But I wanted to point your attention at this guy. So you see, at least for matrices, in fact for operators as well, we have it that. Oh yeah, sorry, I haven't told you one crucial bit of information. For this to work, you assume that E is a finite dimensional projection. Yeah. Here you have to assume that E is finite dimensional. So this B of lambda in this Lipschitz strip is always a matrix. It's a finite dimensional matrix. Technically speaking, no, I'm trying to I'm lying to you because there is this part, but this part it doesn't play any part in what it doesn't matter. This guy, for an operator, will be infinite dimensional. That guy will be finite dimensional, right? So there is always an infinitely dimensional addition to a finite dimensional guy. So, but the main part of the Lipschitz function is always finite dimensional. The part which depends on the spectral parameter. Okay. So anyway, but
what's the
for the operators, you can give it well, actually some meaning to it, properly. All you need to assume is that the range of your projection E belongs to the domain of the operator. Then everything is clear. Then everything is clear.
So you have finite dimensional operator.
Well, the main part of it is finite dimensional. This guy is finite dimensional.
Okay, so but what is the of number?
What is what?
It says it follows the V of lambda equals. Then you have an infinite dimension.
I said that the principal part of P of lambda is finite dimensional. The principal part is this,
right?
This part is infinite dimensional, generally speaking, for an operator. If you start with an operator, I was playing with matrices.
But these operators are from different spaces, aren't they?
Yes, of course.
So how do you add them together?
You just act on the orthogonal sum of two subspaces, why not?
So it's a matrix, right?
Yes, of course.
Well, it doesn't say doesn't show it.
Well, it doesn't show a matrix. Well, you can rewrite it in a matrix form as a homework if you wish. Yeah, I can do it in a matrix way. I don't mind.
Wait, but you think you have an operator, and all of the sub-operators in your block diagram are still operators of the whole space. But if you think of the first dimension in the operator with a big term, and then that's an operator.
As usual, you restrict this guy to a finite dimensional subspace. So, and then it becomes a matrix. Or alternatively, it's an operator in a huge space with a internal.
Yeah, it's okay, but I mean, I'm not sure if it's clear what
Well, okay, I was talking about matrices. In matrix case, everything should be clear. So anyway,
no, because gamma arcs are the different on a subspace.
yes, and they're you redefine gamma to be zero also.
Yeah, but you have.
Okay, sorry about that.
So
But now I have. So all those operators actually act on the same space heap. I hope everyone's happy.
well,
Fine. So still, in the remaining 5 minutes, I wanted to point out this formula to you, and it tells you something. It tells you something. So this is, of course, not a general case, but you will see that in general case, in fact, we have the same representation for things like that. So you see, in more or less general setup already, you can represent this sandwich resolvent as a proper resolvent of a matrix or operator which itself depends on the spectral parameter. And this is not hard to see, right? So what is this now? How can you keep that right? And now the story is different, depending on whether or not you are talking about matrices and linear algebra or differential operators in colors. Although even in the matrix case, you can somehow introduce some, well, basically annotation to do the following. So you can actually always say that B of lambda is a solution operator of an impedance boundary value problem. So yeah, so boundary value problems have been introduced by Hegel. So it means that you've got some sort of a differential or a differential equation with C coming into play, right? So it's a spectral equation. Hegel is just written like Hegel, right? So boundary value problems for such problems have been also written by Hegel, who has shown a number of examples with either Dirichlet or Mortimer or even mixed type boundary conditions. And now I'm going to think to extend.
you have a microphone.
Oh, sorry about that. I'm coming back. So now I'm inclined to think. I'm inclined to extend the class of boundary value conditions even further than Hegel has already done for me. Now let me assume now that in the boundary conditions there is the same spectral parameter which Hegel used to denote by Z, same as myself. But sometimes I do it, I denote it by that. Right. So you have the spectral parameter in two places, in fact, at the same time. You have the spectral parameter where it usually belongs to, which means in the spectral equation, in the differential equation. But at the same time, you have the same spectral parameter in the boundary conditions. You can think of the third type or boundary conditions, which are, say, linear in Z. That would look like the say the normal derivative on the boundary is equal to the spectral parameter multiplied by the values of the function on the boundary, by the traces of the values of the function on the boundary, right? So that would be an example. What do you want to do? I don't want to do that. Sorry. He's done the pictures. So anyway, so a solution operator to such strange problem will be precisely the operator of the cluster incident here. And this is a general result. This is a result due to Abraham Strauss. And that was first published in 1954. And as usual, it's not available. But luckily, his last paper is a survey, and it was published in 1998 in the St. Petersburg Journal of Mathematical Analysis, or Algebra and Analysis of Stone. So that's been translated, and he actually proves there that any operator of this type admits this representation, where specifically B of lambda can always be treated as a solution operator, like a resolvent, and for that reason, it is actually called a generalized resolvent. So I'm finally naming the names, right? A solution operator of an impedance type boundary value problem. But now the same happens for matrices. You might tell me that in a matrix case, there are no boundaries, no differential equations, no nothing. But in fact, although I won't have time to do that for you, you can reformulate everything in terms of matrices as well. You can sort of invent yourself a boundary. For that, you only need to consider two matrix equations, right? The first matrix equation of the pair will be like your equation itself, like spectral equation, right? And the second one, you will just name the boundary equation. Both of them will involve C somehow, or lambda in this setup, but it's the question of terminology, of course. You will be able to call the first of them, the former of them, right? Your spectral equation. The latter will be your impedance type boundary equation. Although I have no time to discuss it any further, although I would like probably, this is very close to the subject area of the so-called Lux spheres. Especially when the Lux spheres are applied to linear equations. So this is stuff like that appears naturally when you apply the subject area of Lux spheres in the Lux for a completely different reason, right? To the wave equation, which is linear. That way, if you do it that way, well, it's well known, and I think I would have seen a book in Spanish published by someone in Mexico. So I could read for the reference, which basically gives the whole details of that story. That way, in fact, using Lux spheres where they don't actually belong by design, you can list, you can explicitly write all the invariants, the whole list of invariants of the wave. So that's useful. And that is done in one page of 2 by 2 matrices, by the way, which is an extra bonus. Okay, so anyway, so leaving that aside again. So once again, what do we have here? We have a so-called generalized resolvent, and the claim is, once again, that any generalized resolvent is can be always realized, whether in the matrix world or not, as a solution operator for an impedance type boundary value problem. This impedance type boundary value problem can be actually artificial. And mostly, like for discrete models, it will be artificial because there is no natural boundary. But if you have a natural boundary, then everything will be even physical. So all the objects will be natural from the physical perspective. And that way, in fact, you can treat, for example, optimization problems, but unfortunately, this will, for that I will right now. So we'll have to design this video. Give us
I did not claim that I would cover this. Like,
no, we won't cover that, but we will cover optimization. So my claim is shortly, just 1 minute, is that using generalized resolvents, you can basically see all those technicalities that we have already told. All those convergences in L1 and stuff like that. So you don't actually need that.
But that was just to illustrate how they form.
So in order to get a form, you don't need that.
No, but
you only need generalized results.
It's not clear whether this approach is more straightforward to get a form.
It is actually.
Yeah.
Well, at least you don't.
But it might be like context. I mean, you get more powerful results eventually for more general systems. But to explain where the form comes from, I actually don't know even the method of asymptotic expansions. I treat it as more complicated than compensated compartments.
A form comes with the nature, by the way.
But takes more space to write it. So compensated compartments.
Well, in fact, explaining the success of the method and where a form comes from takes me just one community diagram of 4 points, right? That's precisely it.
So
anyway, we're going to continue the discussion afterwards, right? Whatever. I can draw you a community diagram to tell you how simple or complicated it is. Well, okay, I at least touched upon the subject area of generalized resolvents, also how we shape the take-home message here is that the subject area is extremely interesting. It has a number of unsolved problems, which are general problems. For example, as I told you, for any generalized resolvent, you can construct a dilation, but there is no concrete way, which is known, of how you do that. So, for example, for dilations of distant gradients, there are three different methods in which you actually explicitly construct the dilation, whereas for generalized resolvent, unfortunately, there is not you can construct it abstractly. This is done in Strauss, as I told you. Unfortunately, those abstract things are not applicable to anything in reality, as usual. So if you go to construct such a dilation in the nature of terms coming from the operator matrix itself, then you will solve the null semi of the function. So far, I have no idea how to do that, by the way.
For your distributed operators, maybe we should get the microphone. Oh,
well, judging by that, well, I think this is better actually.
Yeah, we want to hear the question.
Okay. Can I do it that way?
No, but we're recording. Oh, right. Maybe I should ask. Yeah, just the microphone.
The microphone. This is the. Does it not come with a microphone? That one also has a microphone.
For your distributive operators, the resolvent of the distributive operator is analytic in the lower half plane. What additional properties does it have?
No additional.
Okay.
Now,
Now there's a theorem. There's a theorem that says for a Lena or a Herlotz function in the upper half plane operator value Herlotz function, that always can be realized as the resolving of the subdivision operator. Is there any similar one? No, or is it anything like that?
Okay. So yes or no? First of all, no. The answer is no. So functions are always realized, and this is 9 months period.
So there's nothing special about the resolvents.
It is special, and this is the biggest part. You see, the biggest part is that you can always pass over to a space with a definite vector. So if you do that, if you take a quadratic space, for example, with a finite number of squares, then your distance between non-distance operator will be so much right there. So you will
join with respect to the density of five.
But still everything analytically will hold. So we'll end up with the R function, but that R function will be R function in relation to the definite measure. This is precisely what those guys like the smooth Eastman and the company and Schonten, Schonten mostly from each development. But he was working with the smooth and Eastman. But in the 1990s, they had a number of papers on that, and probably the last bits, like about 10 years ago, maybe 15 years ago, they were doing this as well. Then there is this guy, Sergey Kucherin, Ukrainian working in Germany. He is one of the guys requesting all this stuff on field space methods. And there is a school of in Brazil somewhere, probably Rio de Janeiro. There are the people from partner foundations, part chemical physicists, who are trying to develop so-called PET community quantum mechanics. Probably you heard about that. So the PET symmetric operator is always a J-self-generated operator, with self-generated operators. And then they're using the standard theory, which has been developed by there is this classical book which untypically of those books has been translated into English by Aziz and Yaqino, probably you know that. That's the authors and the name of the book is something like spectral analysis of self-generated variables in the spaces of the something like that. Probably. I can show you a reference. It was translated, sure. Aziz was alive as well 10 years ago. Although it was very old. I went to Moscow. So that's an old classical book. Unfortunately, with the spectral analysis of self-generated metric space, the problem is that on the abstract level, you can only go as far as you can go. And afterwards, it turns out that all the objects of that area are very unreachable applications. Yeah, I know. That's like completely okay. Yeah. The problem is with false spaces. False spaces are notorious. And the notorious source of analytical problems. Analytical simply and some other guys are they're using methods of the computer for starters.
And I think the main issue there is that you have to deal with throwing blocks as soon as you.
Well, actually, the dealing with trouble has the light screen. You don't actually need kind of phrase. Yes or no? Again, sorry for that. But because it was no now. No, the first was no again. As usual. I'm just not no now, right? So essentially, you don't need to go. Certainly, the whole we know that you don't need to go into those spaces because it's much simpler to do the analysis by classical electrode techniques, not the original. So essentially, what he was able to do, I got spectral subspace, which always had been for the German. All the German books I had unnecessarily inside, but there is something else to talk. Like for example,
We maybe should.
yeah, we should talk about the data, and then I'll tell you. And